Hello and welcome to today's webinar. My name is Tyler Reid and I am the Manufacturing Applications Manager here at GoEngineer. Today, during this CAMWorks webinar, we are going to be moving into the fourth axis. Today's 30-minute or so webinar is going to cover some general information on four-axis machining. It's also going to cover a lot of the ins and outs of programming in fourth axis, specifically inside CAMWorks. I wanted to do a webinar on the fourth axis because I've been hearing a lot lately about four-axis machining, and it sort of has an allure to it. And it's perceived by a lot of new CAM programmers as being extremely difficult, maybe to learn and to implement and to use effectively. But I don't necessarily think that's true. I think it's a lot simpler than people give it credit for. So I wanted to do a quick webinar and show just how simple it is. There's many different types of four-axis machines. So to say we're machining in four-axis is maybe not all the information we need to actually know what's going on. So I wanted to make everybody aware that in today's webinar, we're going to be covering milling in four-axis. There's other types of machines that also are capable of four-axis. In turning, you can get four-axis by having both a front and a rear turret. So you have a 2+2 setup. In a mill turn machine or a lathe with live tooling, you can get to four-axis either through your live C spindle and a Y-axis, or that should say your C spindle and a W-axis, a sub-spindle. And then even wire EDM, you can get four-axis, and that's usually set up as what's called a land and taper. That's two XY mechanisms stacked together so you could create tapers. But today we're going to be talking about four-axis milling. I broke that down into three different categories: indexing, wrapped, and simultaneous. So we're going to touch on each one of those specifically. We're going to tackle four-axis indexing first because it really is probably the most basic type of four-axis machining. But that doesn't make it any less useful. Indexing on a fourth axis gives you all the benefits of four-axis parts on, parts that might only have 2.5 or 3-axis features. Some of those features are reduced setup time. That reduced setup time is going to be mostly as a factor of reducing the number of setups. So, for example, if we have a part that we have to cut on 4 different sides, we might only have to do one single setup as opposed to 4 individual setups. Fewer setups means we're increasing our accuracy. We're going to be more reliable and probably less scrap as well on our parts. And we're absolutely going to reduce the cycle time. Even when you take out the setup time, our cycle times are going to be faster as well. Indexing can be done on single parts alone. So you might have a single part chucked up, or what's really common is using a tombstone type fixture. I have an image here of a tombstone on a horizontal machining center. We're going to cover that example. But there's a part where, because of that four-axis machining, we're only machining one side of a part, maybe technically at a time, but we can chuck up 8 different parts at the same time. You'll see, if you're an experienced CAMWorks user, you might have already been doing this indexing on accident, and there's really only a couple steps that you need to do if you're already programming a part in full. One super good benefit for indexing is that automatic feature recognition is available. It works just as well on an index part as a part that we're going to be flipping manually. So we're going to jump in. We're going to take a look at a couple index parts. So because the focus of this webinar is the four-axis portion, I'm not going to program these parts entirely. We're going to focus on the indexing. Here is a standard pump housing. This might come in as a casting with only some surfaces to be machined, probably a lot of the holes in the mating surfaces. I am going to run automatic feature recognition on this and just try to treat it as a normal part initially. Note that we're in part mode and I'm just programming one part on its own. The feature recognition is probably going to do a decent job on this part. Most of the features are pretty cut and dry. You can see that we have 6 different setups, so that corresponds to the 6 different sides of the parts. On each setup, we have some hole groups. So we have a countersunk hole group, some pockets. Did a pretty good job. I don't think I have the face feature turned on to be found under the automatic feature recognition. So I'm going to go ahead and accept this and say generate our operation plan. And that's going to run all of our features through the technology database. The TechDB is going to take some information on the features and sort of dictate how we might cut those features. It's going to spit out operations, things like center drills, countersinks, rough mills, contour mills, all of those tools. So right now I'm 3 clicks in and I have a lot of toolpath. I might do a quick simulation and just see how close we are. Again, I'm not going for a perfect part here. What I'm going for is the indexing. But as far as the 2.5 axis features, it looks like we're doing pretty good. A lot of this curvy stuff, assuming it came in as a solid block of billet, we would probably have to do some 3-axis machining. If it came in as a piece of a casting, then I could read that in as my stock shape. We have other YouTube videos on how to do that. So what I want to do now is just talk about the actual indexing. If I was going to be cutting this part without an indexer, without a rotary axis, I would take each setup and I would post out G-code separately for each setup, most likely. Or I would insert program stops through a right-click menu, new post operation, program stop. I can insert that, and I can place that program stop at the end of the setup, and then post out maybe these 2 setups as one program. And it will stop, and I could add some instructions to that post operation. Say add a comment here, flip part, whatever instructions I need to my operator. That's the long way of doing it. So if we have indexing, all we need to do is tell CAMWorks, you can reach different setups through the use of a rotary axis. So we do that in the machine dialog. Under setup, I'm going to select, in this case, 4-axis indexing. And when I do that, it's going to give me some options on my rotary axis limits. Some rotary axes can rotate a full 360 degrees infinitely. Some might only have, say, a minus 110 plus 110 degree range. That's going to be important to tell CAMWorks because CAMWorks is going to use this information to reach different setups, whether or not it's going to go clockwise or counterclockwise to reach those setups. I'm just going to assume that I have an infinite full 360. Next, I'm going to want to go to the rotary axis tab and actually tell it what orientation my rotary axis is in. There's a couple ways to do this. I'm showing you the simple way first, and that's just to use faces on the model. So if I click this circular face, I can set it concentric to that face. This arrow is going to point to the positive direction on whether or not this is the y-axis or the x-axis. So if I was going to chuck this up and my rotary axis, if I was looking at the part from this direction on the machine and my rotary axis was on the right-hand side of the part or even the left-hand side of the part, the positive direction is going to be opposite of what I'm looking at. Okay, assuming I'm on the x-axis here. I can specify a rotation direction if I want to limit it to either going clockwise or counterclockwise for one reason or another. I can do that here. And then it needs to know a part 0 or a 0 plane. I'm going to go ahead and use a flat face on the model to select that. Okay, that's basically it. Beyond making sure that our part zeros are in the correct spot, this is all that there is left to do. When it comes time to doing the part zeros, what we'd want to make sure is that they're in the same spot on all different setups. So on this particular part 0, we're in the top center of the model. We're going to want to make sure that that corresponds to every single setup around the block. When we post out our code, let's make sure I have a 4-axis post selected. I did not. So if you're posting code and you're not seeing A or C or B moves, make sure that your post is enabled for 4-axis. I'm going to go ahead and use the tutorial post. If you have a post provided by GoEngineer, it may not have the multi-axis implemented. If you didn't have a rotary axis at the time that we delivered the post, it probably doesn't have it active. So if you add a rotary axis, or if you want to start using a rotary axis, contact us and we can update your post. So now when I post this code, what we're going to be looking for are rotary moves. So here's our code, and we have an A and B. So A minus 90, B 0 initially. And if I just do a search here, A, we see an A0 on center drill 3, which is at the beginning of setup 0. So our first setup from this direction was minus 90. Remember, I set this as my 0 plane. So when we got to setup 2, we went to A0. So there's 4-axis indexing. You're programming the part essentially the same. You're just automating the moves between the rotary axes. We can do this in an assembly as well. So if we take a look at this Tombstone setup that I put together, we have 8 of the same parts set up on our Tombstone. And we actually have access to a few of the sides as well, depending on what direction we are facing. So from one direction, we can actually machine 3 different sides of the part. When machining in assembly mode, we have the option to program the parts on their own in part mode and then import that data into the assembly, or we can program them from scratch in the assembly. And that's what I'm going to do here. But this is, again, going to be pretty much an automatic feature recognition setup. What we need to do is we need to tell CAMWorks what parts we want to machine. So I'm going to say that part there, and I'm going to tell it to grab all instances of that part. One thing that I have done beforehand is I have set up a coordinate system. And this is how I'm going to dictate to CAMWorks what axis is the rotary axis and what orientation it's in. So in the machine window under setup, notice I already have it set to 4-axis, and I also have a coordinate system input. Okay, we'll explain that in a minute here. Under my rotary axis, I have it set to the Y-axis in this case, with positive pointing up, so we're on a horizontal machining center. Real quick, in the assembly feature tree, notice I have a coordinate system down at the bottom of my fixture plate. That's a SOLIDWORKS coordinate system, and we're going to be creating those, a couple of those later on here. But within the assembly, it's found under Reference Geometry, Coordinate System. It's going to give you some boxes to help you place and orient those coordinate systems. I will usually create just a simple sketch, pick a point for the center, and then pick a couple lines or edges on the model to align the X, Y, Z axes. Okay, so we're going to run the automatic feature recognition on this. I think it's going to take a few seconds here. It's going to be grabbing all of the features on these parts, it will grab features even on the back sides of the parts, but it won't allow me to machine those because I can't access them. We'll run these through the database. So one of the reasons why I wanted to show this indexing in the assembly is I wanted to show a couple sorting options that we don't have in the part mode. So notice in the part mode, we basically machine one setup at a time. So we machine an entire face of the model, then rotated it, and then machine an entire face. That's not the most efficient way of doing it. There's ways that we can get around that, but they're not automated. Whereas in the assembly mode, they are automated. And we can get maybe fewer tool changes, for example. Let's go ahead and generate this tool path. So we have all the toolpath on here. When in the assembly, when we go to sort the operations, we now have the option to do by the setup, across the setups, or by and across the setups. So that means, are we sorting only within a setup or across all setups at the same time? And when we do that, we can sort by, say, the tool. We can rearrange our tools in the order that we want simply by dragging and dropping them. So I might take a countersink and move it all the way up, for example, and then hit apply. And what we'll see over on the left-hand side are many different setups that are all split and linked together now. That's a lot of tools for just a few clicks. When we simulate this, notice we only see our parts there. If we want to add the tombstone as some like a fixture, we can do that as well. We're at our tombstone, add our vices. We'll tell it to grab all our vices and also this fixture plate. A little bit better simulation, and when it simulates, it will also, as it's doing its collision checking, it will now check for collisions with the vice and the tombstone and whatnot. So notice that now we've minimized the number of tool changes because it's actually rotating before it changes the tool. We can do that in the part mode as well, but what we have to do is we have to say, go into a setup, right click on the setup and say split setup. So now we have two copies of the same setup, and then we could move, say, operations, drag them down to the other setup. So it's a little bit more manual. I should say it's a lot more manual. For that reason, if you're doing indexing and it has a lot of tool changes, you might want to consider bumping it up into an assembly. And you don't need to add the fixtures, it's just bring it into an assembly. All right, the next type of 4-axis work is called wrapped features. And wrapped features are really a subset of the simultaneous option that we're going to be talking about next. It is simultaneous cutting, but it's simplified. It's taking advantage of a geometry, okay? When features are concentric to the rotary axis, that greatly simplifies the toolpath. It's almost as if you take a 2.5 axis feature and just wrap it around the part. And that's basically what CAMWorks does as well. And it allows you to treat these features as if they're 2.5 axis, which simplifies the programming. One caveat here is that the tool is always going to point towards the center of rotation, okay? And it's going to affect a little bit how, it's going to affect what features you can cut accurately in terms of, say, the sidewalls and draft angle and stuff like that, which we will see here. When you're using wrap features, you're definitely trading off between simplification on the programming side versus capability on the machining side, meaning you're sacrificing some capability in order to program it quicker. You have reduced control over the tool positioning, but we're going to be able to spit these out pretty fast. The type of wrap features that we can do are pretty similar to the 2.5 axis features. We can do pockets, bosses, slots, open profiles, and engraving. Notice on each one of these that the features are concentric to the rotary axis. Okay, that's the key thing for a wrap feature. And that's when you see that, that's going to be a signifier that, okay, I can use a wrap feature to program this. We're just going to do a couple parts here, just so you can see how simple these are. This one has some pockets. So notice I do have my coordinate system on the front of the part there. Inside the CAMWorks feature tree, we want to go to Setup, 4-axis, and we want to read in the coordinate system. If we don't do these steps, then CAMWorks is not going to give us the option to actually add a wrap feature. We're going to create a new mill part setup. And now in the right-click menu, we have new wrap feature as an option. If you notice, my setup is in this direction, and that doesn't even really correspond to the direction of any of my wrap features. That's okay. The setup direction doesn't have to be directly on top of the wrap feature. The setup is just the starting position. So new wrap feature, the menu is going to look pretty similar to the 2.5 axis menu. We choose our feature type, pocket, boss, slot, open, profile, or engrave. We'll go pocket. We're going to select the bottom face, end condition, top face. This is exactly like the 2.5 axis menu. But notice there's a couple things here. If we look at the actual lines of the feature, they don't line up with the lines of the model. What's up with that? Well, this is where you get a mismatch between how a part is designed versus how it has to be cut. Okay? My guess is that whoever designed this part probably used the SOLIDWORKS wrap feature, which doesn't create features in the same way that a machinist might cut this pocket, especially if we're locking the tool on the rotary axis. If we're locking the tool on the rotary axis, we can't taper a wall. We just can't do it. And so that's one of the caveats of using this wrap feature. If you got a part like this in a drawing and your CAD model and you start programming it and you notice this sort of behavior, you might have to go back to whoever designed it and ask, do I really need to follow this surface directly? If you do, then we're going to have to use the full simultaneous 4-axis multi-axis feature. If they don't, then you can do the simplified feature with the wrap feature. And if they don't, you might want to tell them to draw their parts more accurately next time. So there's my wrap pocket. It's going to behave pretty much exactly like a 2.5 axis pocket. Let's do a slot real quick. Make sure we have our rotary axis set up, 4-axis coordinate system. We will do our new mill part setup. This time it's a slot. We're doing a slot so that it roughs out the interior. If we only wanted to do this outer wall, we might do something like an open profile. Again, you'll see a bit of a mismatch here. We're going to overcut on this wall. And we're going to be overcutting on a lot of the walls. Because these walls are not lined up. They're not tapered down towards the center of rotation. You see that? This wall is actually straight up and down. So it would pass just to the right of the center of rotation. Most people, when they design features like this, they don't think of that. And they just assume that SOLIDWORKS is going to draw it correctly. So in most cases, you're going to be fine with the wrap feature. But you're always going to want to ask. There's our roughing cycle. And if we simulate that, we can see our 4-axis movements. Sometimes in CAMWorks, when you simulate the 4-axis, the tool moves and sometimes the part moves. That doesn't really affect how the G-code is posted. Probably need to bump up the accuracy on that one. So those are wrap features in a nutshell. They're not always applicable, but when they are, they're going to be a time saver. Especially if you've already been using the 2.5-axis software extensively and you're already familiar with the rough and the contour mills and the options that they have. So that brings us to 4-axis simultaneous. So 4-axis simultaneous means we're going to be potentially cutting and rotating the part at the same time. And the tool doesn't have to be on center. It can be pointing off the rotational center. So 4-axis simultaneous, the way we're talking about it now, could actually cut those previous parts accurately. This is useful for cutting continuous surfaces, say all the way around a part. We're going to be looking at a prop here in a bit. We have full tilt control over the tool. This is important. This is something you don't have when you're using a wrap feature. We can add side or tilt angles to improve the rigidity of our tool, improve the tool life, reduce the cutting forces on our tool, and improve the surface finish. And what I mean by that, if you take a look at the image on the bottom right-hand corner, you see a ball nose mill with some inserts, and it's tilted at a certain angle so that the area that the tool is actually contacting the part is not on the bottom center of the ball nose. And that's going to mean a lot of things. One, it's going to mean that we have more constant rotational speed or more constant surface feet per minute, because on a ball nose, and on any tool really, the dead center of the tool has almost no speed at all. And as you go to the outer edges of the tool, that rotational speed increases. So by only using the edge of the tool or using most of the edge of the tool, that's going to give us more consistent cutting. It's also going to position a tool so that it can better handle bending forces. So that's where you're going to get your improved rigidity. And from improved rigidity, you're going to get better surface finish. So that's one of the main benefits of rotational machining or multi-axis machining in general. Even on 3-axis parts, you might tilt it for those reasons. The 4-axis simultaneous is the most complex 4-axis CAM skill because with more control and more functionality, you're going to have more options available to you. So let's start with this propeller. This is a pretty typical type of example. This is a propeller I cut a couple years ago. And I pulled it out today because it's a pretty good example of some of the 4-axis stuff. So I'm starting pretty much fresh. I have the rotational axis already set up. My stock is set up. It's just bar stock, a rectangular stock. And I have a mill part setup, okay? Under the mill part setup, notice it does give me the option for wrap feature, but we don't want that. What we want is a new multi-surface feature. If you've been using CAMWorks for 3-axis machining, you'll notice this is the exact same type of feature. There's a couple ways to create these multi-surface features. You can just select faces you want to cut. You can use all displayed, which creates a feature out of your whole part. We can also do faces by color or an STL file. In this particular case, I'm just going to select the couple of faces I want to cut. I want to cut this face, and on the back side here, that trailing edge. Under my strategy, I'm going to select 4-axis. And notice what that is going to create is something called a multi-axis mill. This is a new type of operation. You may have used it in the 3-axis module, but chances are you haven't. So in 4 and 5-axis, we only have one feature type and one type of operation, multi-surface feature, multi-axis mill. Within that one operation, we have all of our options. So we don't have a rough mill, we don't have a contour mill, we don't have Z level, we don't have any of that, just multi-axis mill. We're going to generate an operation plan. We're going to bump into this multi-axis mill. And right away, you're going to notice that you have a lot more options, many more tabs than you would normally see in, say, a rough mill or a contour mill. Some of the tabs are the same, like this tool tab, the feeds and speeds tab. Those are pretty much the same. This pattern tab would be the equivalent to, say, the roughing or the contour tab. It's going to control the shape of the tool path. I'm going to give you my standard workflow on what I like to do. I like to make changes piecemeal, and I like to hit preview a lot. 3, 4, 5 axis programming, there's always just a few things I do initially to set it up, and then I start making minute changes and programming it visually. So in 4 axis, normally what I do is the first tab I go to is axis control. I make sure it's set to 4 axis, but notice we can limit this to 3. So we can actually do 3 axis and have a lot of options. We can go 4 to 5. I'm on 4. I want to make sure it's rotating around the X. That's all good. This checkbox here, point tool to rotary axis, that would simulate a wrap feature. In general, I'm not going to keep that checked. And that's going to allow me to actually orient the tool relative to the surface it's cutting. Most common is normal to surface. So that means the tool is always going to be normal to the surface. It's always going to be perpendicular to the exact point on the surface it's cutting at that point. If I wanted to add a lead or a lag angle, like we were talking about, I could say tilted relative to cutting direction. I can add a lead or a lag angle here by doing a positive or a negative angle. Other options, there's numerous. If you're not quite sure what an option means, say tilted around axis or tilted through point, you can click it and it's going to give you a little bit of a visual there. And for example, this one's going to allow us to select a point, and then the tool is always going to be tilted from that point. Okay. In most scenarios, I would say probably 85 to 90% of the time, normal to surface or tilted relative to cutting direction with a slight lead or a lag angle is what you're going to want to do. A lot of these other options are more job specific. Something like porting, for example, you might do tilted through curve and have that curve go down through the center of the port. Something like that. I'm going to go ahead and use normal to surface. Some other options in here, I can limit the tool angle, and when I limit it, I can limit it in ZX, ZY, different planes. We're just going to be covering the basics here during this webinar. If you're really getting into 4-axis machining, I definitely recommend contacting us and setting up maybe a day where we could have one of our experts come in and help you on site. So after I'm done with the axis control, I like to go into the links, and I like to basically tell them all to rapid retract to rapid distance. And that's going to help me spot the links. I don't think there's any in this part here. What links are is their movements between the tool paths. And sometimes if it's set to direct or if it's set to follow the surfaces, it's hard to see where they actually are. So I like to pull it off the part. Another thing I like to do is set my lead ins and my lead outs to 0. Okay, this is again just an initial thing that I like to do, and then it helps me read what's going on. And then lastly, I actually get to my pattern. Pattern is where you're going to dictate, what sort of path this tool takes over your part. The equivalent in 2.5 axis would be pocket in, pocket out, spiral, radial, those types of options. In 4 axis, we have slice, which is similar to zigzag. Cut across curve, which would allow you to select a curve and make cuts perpendicular to those curves. Flow line between curves, which is I think what I'm going to do on this part. So I'll talk about it in a second. offset from curve. This would allow me to say select a curve, say this curve on the end here, and then just offset the tool path down the length of the feature. So if I hit preview, we let this process and we can see it's offset. This is a straight line, so it's not that interesting in offset, but notice over here, it continues to be straight. We don't actually cut into this. We do gouge it a little bit. We can get around that. For this reason is why I probably wouldn't want offset curve. Now there's methods around this, but offset curve is just trying to make it work is probably not what we want to do. Something like flow line between curves, that's going to allow me to select two curves. Say that guy here, this end. Notice I am selecting two segments to make one curve. It's totally fine. And then this guy over here. And what this is going to do, it's going to interpolate my tool paths between these two curves. It is going to change the pattern on the part. We're not going to get those straight lines only. Notice how they do start to curve right around this position here. Maybe just past the midpoint. They start to curve until they're fully conforming on this end. Okay. I do have a slight link here. All of these retracts are links. And this is the point where now I might say, let's deal with the links. If you've been using links in 3-axis, you know the link menu is really simple. You set a number, and if the link distance is above that number, it retracts. And if it's below that distance, it follows the curve. In this case, we have a lot of options. We have links along the cuts. We have links between the cuts. And then for each of those types, we can tell it what to do if it's above the threshold or below the threshold. I'm going to go ahead and say follow surfaces if it's below the threshold, which is 20% of the tool diameter. And now it's going to basically do a step over between passes. Good enough for this purpose here. Couple other things that you really need to think about on the 4-axis. Under the entry and retract, your clearance plane cannot be a plane in general. In general, your clearance plane, you want a cylinder. So in this case, since our rotary axis is on the X, we want a cylinder about X. We didn't get into trouble on this part, but you absolutely can get into trouble. We just happen to start and stop on the correct sides of the part. So you actually want it to be a cylinder so that it doesn't try to pull through your part to reach a plane. So notice how that changed the direction we're approaching from. And then lastly here on the pattern, we want to, in this case, we probably want to do zigzag. But there's a couple things we want to do on the limits. So we actually don't want to cut to the very edge of this feature because we're going to gouge this part. We can get around that a couple different ways. We can tell it to avoid cuts at the exact edges. And if we have that, which is what we do, it will offset by the radius of the tool. But it also offsets by the radius of the tool on this side. So it doesn't cut to the end. A lot of times what we'll do is we'll say start at the end or start at the exact surfaces, and then we can set separate margins for the start and the end here. So we might say the end margin is the radius of the tool, which is a 1/2 inch diameter. So end margin 0.25, something like that. Also under this menu, we can tell it to limit the number of cuts. This is really useful. If I wanted to just do one cut along an edge, say, I could just limit my cuts here. If I was cutting from this direction outward, and I really wanted to fine tune this radius, come in with a smaller tool, I might do that. I'll say number of cuts limit it to 5, something like that. How we process our step over is normally by the max scallop size. So right now I have it set to 5 thousandths. That would be pretty coarse. If I wanted a fine surface on this propeller, what I ended up doing, I think, was 2 10,000ths of a max scallop. I'm not going to do that here in the demo because it's going to bump up the processing time quite a bit. Notice I only programmed the finish pass. That's pretty typical for this multi-axis work. Within this multi-axis tab, we do have the ability to add roughing passes. So once I finish the tool path on the surface itself, then I might come in and add roughing passes. I'd say multi-passes. I can add the number of passes and then also the depth per pass. Okay, so with that, that's the intro into 4-axis machining inside CAMWorks. The big takeaways here are you have indexing, you have wrap features, or you have simultaneous features. Those step up progressively in complexity, but also functionality. A lot of parts that you cut are going to be a combination of those. They're going to be 2.5 axis, maybe 3 axis, plus indexing, like the pump housing. If you have any other questions, you can reach me at my email, Reid at GoEngineer, or you can find me on LinkedIn. Definitely check out our YouTube page, youtube.com/GoEngineer. We have lots of videos like this and more quick tip videos as well, 3 to 5 minute videos. Thank you guys for watching.